Okay, so today we're going to look at section 8.5, ratio, root, and comparison test. And our goal here is to develop new ways of deciding whether or not a series, AN, converges or diverges. So that's our idea. So at this point, we don't have too many ways of actually doing that. If the series is a geometric series, well, we can do that. If the series is one where we can use an integral or divergence test, well, then we can do that as well. But those are the only options that we've got at this point. Today we're going to look at three more types of things, there's actually four in here, that allow us to decide on a much greater class of series, whether or not they converge or diverge. And so let's start with the ratio test. The ratio test. So this is, I'm not going to prove that this works. Again, this proof is in the textbook, and if you really want some help understanding that, I can certainly provide that. What we're going to do is talk about the procedure, how to apply it, and practice it with a bunch of problems. And it goes like this. So here's our ratio test. I'll write it down, and then we'll apply it to a bunch of problems. And we're gonna start with a series, AN. All right, we want to know sum of AN. We want to know if this converges or diverges. So what I'm going to do is make the following. I'm going to create the following. I'm going to look at the ratio of the term compared with its next term. So I'm going to look at AN plus 1 divided by AN. All right, so this is like the 101st term divided by the 100th term, and the 107th term divided by the 106th term. So I'm looking at the ratio. So I want that ratio to get small, because if that ratio gets small, well, then that means that the series is going to zero quickly. So what I need to do is take the limit as n goes to infinity of this and see what happens. And so then there's a couple of technical things in here. We actually need to take the absolute value. So the limit as n goes to infinity of the absolute value of AN plus 1 divided by AN. And let's call that limit L. Since it's an absolute value, it's always a positive number. If L is between 0 and 1, but not including 1, then I can conclude that the series converges. Because that means that these ratios get small because they get less than 1. So the ratio gets less than 1, so these terms are going down quickly enough. If the limit is bigger than 1, including infinity, then it diverges. And if the limit actually equals 1, it's inconclusive. And this is it for the ratio test. This is our procedure. It gets a little complicated in some situations. So let's just practice it with a few basic examples. All right, so let's look at this series. We'll look at the series 1 over e to the n. This is one that we already know what to do with. We actually looked at this series with the integral test, and we decided that it should converge. Let's try to apply this ratio test as well. Let's use the ratio test. And again, it doesn't matter where I start, so let's just start at 0 and go to infinity. So AN plus 1, I plug n plus 1 in for n, and I get 1 over e to the n plus 1. AN is just our formula for the terms is just 1 over e to the n. So AN plus 1 over AN is 1 over e to the n plus 1 divided by this, which is multiplied by the reciprocal, which is e to the n over e to the n plus 1. But if I have e to the n in the top and e to the n plus 1 in the denominator, well, this is just like e to the n with an extra e, so I actually get just 1 over e. Remember our next step, take the limit as n goes to infinity of the absolute value of AN plus 1 over AN see what we get. Well, the absolute value, so this is just the limit as n goes to infinity of the absolute value of 1 over e, based on our calculations over there. But that's already positive, so the absolute value doesn't matter here. But in this case, what happens as n goes to infinity? Well, I don't have any n's in here at all. I just get 1 over e. But 1 over e is less than 1, and that's what we're looking for when we apply the ratio test. Take this limit, see what you get. If it's less than 1, that tells me that the series converges, which is what we also concluded using the integral test. So let's use the ratio test for 1 over n squared. Remember that we decided using the integral test that this one should in fact converge, should also converge, 1 over n squared. It's a p series where p is bigger than 1. So they should converge. If we apply the ratio test, we're looking at the limit as n goes to infinity of the absolute value of an plus 1 over an, which is the limit as n goes to infinity of an plus 1 is 1 over n plus 1 squared. I'm plugging n plus 1 in for n. Divided by an, which is 1 over n squared. Again, everything is positive, so I don't have to worry about the absolute values. But this is the limit as n goes to infinity of 1 over n plus 1 squared, the numerator, divided by a fraction is multiplied by n squared over 1, which is the limit as n goes to infinity of n squared over, let me expand this out, n squared plus 2n plus 1. This is a limit we can calculate. We look at the highest degree terms. We see n squared over n squared, which is 1. So this limit is 1, and so according to the ratio test is inconclusive. All right, so we can see that our different tests might give us, some things will be inconclusive. Ratio test is inconclusive, so we have to fall back to the one which we already knew for this situation, the integral test. So you may have an inconclusive test for using one test, and so you have to use a different test instead. Okay, so before we look at some more, we're going to see a lot of things in the future here where we have this factorial, and we'll see why, but factorial is going to start showing up a bunch, and so we're going to look at a bunch of series now that have a factorial included. Remember what factorial means? If I said 10 factorial, then I'm saying 10 times 9 times 8 times 7, 6, 5, 4, 3, 2, 1. So that's what factorial means. So n factorial is n times n minus 1 times n minus 2 times all the way down to 1. So let's look at this series. 1 over n factorial. I can actually start at 0 if I want, because 0 factorial is 1, remember. So let's use the ratio test. Alright, so limit as n goes to infinity of an plus 1 over an. I'm going to start skipping a few steps here. An plus 1 is 1 over n factorial, n plus 1 factorial. Plugging n plus 1 in for n. If I divide by an, that's multiplying by the reciprocal, so that's n factorial over 1. The absolute values are gone because everything is positive. So that's the limit as n goes to infinity of n factorial over n plus 1 factorial. Now we have to be a little bit clever. Remember that n plus 1 factorial is n plus 1 times, what would this be? N plus 1 times n minus 1, and so on and so on and so on. So we're going to see this happen a lot. This is n plus 1 times n factorial. So n plus 1 factorial, I could start with n plus 1 and then move down, but if I move down, what's left over is n factorial. And the reason that I do that is so that I can cancel, and I get the limit as n goes to infinity of 1 over n plus 1. Now, as n goes to infinity, the denominator goes to infinity, so this limit is 0. But 0 is less than 1, so the series converges. Okay. Let's move to the root test, which is again an alternate test, another test that we might use in certain situations. And we'll talk about when you would use one test versus another when we've talked through all of these. The root test is another test. It's just a separate thing where we'll apply a different procedure, and it works like this. So we're looking at the series sum of an, and what we're going to do is we're going to take the limit as n goes to infinity of the nth root of an. And let's call that, well, L. And now our conclusions are actually the same as in the ratio test. If L is between 0 and 1, by the way, the only way to make this actually work, if I want to take nth roots, I can't have a negative thing, a negative an, so an needs to be bigger than or equal to 0 for the root test, which means that I can't have a negative limit anyway. So if L is between 0 and 1, but not including 1, it converges. If L is bigger than 1, it diverges. And if L equals 1, it's inconclusive. Okay, so let's look at a few. Okay, so how about sum of as n goes from 1 to infinity, sum of 1/3 to the n. Let's use the root test. According to the root test, we want to take the limit as n goes to infinity of the nth root of 1/3 raised to the n. But remember what the nth root is. The nth root is the 1 over n power. So this is still the limit as n goes to infinity. Now, how do exponents work? If I have something to a power to another power, I'm multiplying the exponent. So this is a limit as n goes to infinity of 1/3 to the n times 1 over n, which is just 1/3. But as n goes to infinity, that limit is just 1/3 because there's no n's at all, which is less than 1. Since our limit is less than 1, we conclude that it converges. So here's one situation in which a root test is going to be useful. If I have something raised to the nth power. Because if I'm raising to the nth power, then when I apply the root test, then I'm re-raising to the 1 over n power, and so the n and the 1 over n will cancel off, and we'll have something which is hopefully simplified. So let's look at another one. A sum of k squared over 2 to the k, as k goes from 1 to infinity. Now this is a little bit different, but I do see this 2 to the k, which means that possibly the root test will work. infinity. So we're looking at the limit as k goes to infinity of k squared over 2 to the k, all raised to the 1 over k power, which is, when I take these, I'm going to get k to the 2 over k, all over 2. Because the k and the 1 over k cancel out. The limit as k goes to infinity. And this is the limit as k goes to infinity of k to the 1 over k squared all over 2. Now, this is a funny limit that we're going to see a bunch of times, so we just have to remember what happens. Right? So what happens here, the limit as k goes to infinity of k to the 1 over k actually just happens to equal 1. So this is something that we're not going to prove today. You may have seen it back in a Calc 1 class when you were talking about limits, but it is true. This limit is 1, which means that the limit of this whole thing is going to end up being 1 squared over 2, which is 1/2, which again is less than 1, so it converges. Okay, so we'll look at this one. 1 plus 3 over k, all to the k squared. Again, we see a power of k, although in this case it's k squared. So we're still going to use the root test. So we take the limit as k goes to infinity of 1 plus 3 over k to the k squared, all to the 1 over k. If I take this all to the 1 over k, then I get k squared over k, which is k. So the limit as k goes to infinity of 1 plus 3 over k to the k. And remember that this is something that we saw a few sections back, this limit of 1 plus, we saw a couple of things, 1 plus 1 over k all to the k, remember it was actually e. But because of this 3 here, we actually get e cubed. Right. Now, e cubed is bigger than 1, so according to the root test, this diverges. Okay, so we will move to our comparison tests. There's really 2 different types of comparison tests. The first we're just going to call a regular old comparison test, and there's nothing real tricky about this. It just says that if I have 2 series, sum of an and sum of bn, right, and both are positive, so an is bigger than 0, and bn is bigger than 0, and also if each term an is less than or equal to the term bn, then if bn converges, so does an. All right, so if I'm less than a convergent series, then I converge. No trick there. If an is bigger than bn, and sum of bn diverges, then so does sum of an. So if I'm bigger than a divergent series, then I diverge as well. So this is exactly like we saw when we talked about improper integrals. And so this is good for a couple of situations. So for example, remember these. We saw something like this. Sum of 1 over, say, n minus 1 from n equal 2 to infinity. Well, n minus 1 is actually less than n, so when I move to 1 over, the sign of the inequality flips. So 1 over n minus 1 is bigger than 1 over n. Sum of 1 over n, therefore, is less than sum of 1 over n minus 1. This diverges. If I'm bigger than divergent, then this must diverge as well. And this is the basics of the comparison test. I compare this to something that I know. If I want to just conclude that this diverges, I better be bigger than something that I know diverges. We can also do something in the other direction. If I said, what about sum of 1 over n squared plus 1 from 1 to infinity? Well, then I would say that 1 over n squared plus 1 plus n is actually less than 1 over n squared because I have a bigger denominator now. But sum of 1 over n squared is a p series with p bigger than 1, so it diverges, so it converges. And so I am now less than a convergent series. So that means I can conclude that this thing converges. Now, remember that we have a couple of things that end up being a little bit trickier. If I can't compare exactly the way that I want, we have to use what's called the limit comparison test. So for instance, if I were looking at this series, sum of 1 over n plus 1, the problem is that 1 over n plus 1 is actually less than 1 over n because I have a bigger denominator. If I made this into a series, it would diverge, but being less than a divergent series doesn't mean anything. It could still diverge, but it could be so much less that it's finite and it converges. We certainly want to feel like this one still diverges, but the straight comparison test doesn't work. And so we have to apply what's called the limit comparison test, which says this. If I have two series, so the comparison test in this case is inconclusive. So the limit comparison test says that if the comparison test is inconclusive, so suppose that I have two series, sum of an, sum bn, both of which are bigger than 0, then what I'm going to do is I'm going to say if the limit as n goes to infinity I'm going to consider the limit as n goes to infinity of an over bn. And I'm going to call that limit L. So then a couple of things could happen. So if L is a finite number, right? So if L is finite but not 0, so it's above 0, it's also below infinity. So it's finite but not 0. Then an and bn both have the same property as far as convergence goes. Then the series an converges if and only if the series sum bn converges. So if this limit is finite, then they have the same convergence property. Either they both converge or they both diverge. If the limit is 0, then we look at bk. bk, remember, was our bn. bn was our denominator, remember. So if this limit is 0, then and sum of bn converges. Then if bn converges and I have this limit as being 0, that we want to think about that as saying that an is actually less than bn because the limit has to end up being 0, so an has to be smaller, the top has to be smaller than the bottom. So if the limit is 0 and bn converges, then we can conclude that an converges as well. And if the limit is infinity, then we're looking the other way around. If the limit is infinity, then we're looking at the opposite here, and bn diverges, Well, that means that an must go up to infinity faster than bn, so I can conclude that an diverges as well. So these are 3 possible conclusions for the limit comparison test. And they look kind of complicated, but they're really not that complicated. Let's just apply it in a couple of examples. And let's start with the one that we began with. Sum of 1 over n plus 1. So we want to compare this to, or limit compare to 1 over n, because we feel like it behaves just like 1 over n. So we're going to let we're going to let an be 1 over n plus 1 and bn be 1 over n. And then we're going to look at the limit as n goes to infinity of an over bn, which is the limit as n goes to infinity, of an, which is 1 over n plus 1, divided by bn is multiplied by its reciprocal, but the limit of this is n over n, which is 1. So we got a finite limit. So 0 is so L is bigger than 0 but not infinity, which means that both of these series have the same convergence property. So now I can say that since 1 over n diverges, 1 over n plus 1 diverges as well. And that's the basics of this section. There's a lot of different stuff going on in this section, but we've covered the basics, and so I will see you next time.